First, let us recall the vectors of the real plane, which is denoted by R2. It is the set of ordered pairs A, B, where A and B are real numbers. Note that addition and scalar multiplication of vectors are consistent with those of row matrices or column matrices. Let's compare. For addition, to add two vectors x1, x2 and y1, y2, we add the corresponding components to get x1 plus y1, x2 plus y2. For row matrices, we add the corresponding entries. So if we have x1, x2 plus y1, y2, we get x1 plus y1, x2 plus y2. So we see that this is very similar to the addition in vectors. It is just that we don't have a comma to separate the entries in a row matrix. For column matrices, it is the same as row matrices, except the entries are written vertically instead of horizontally. Let's also look at scalar multiplication. For vectors, when we multiply a scalar k to a vector x1, x2, we multiply each component of the vector, so we have k times x1, k times x2. For row matrices, we multiply each entry of the matrix by k, so we get kx1, kx2. Again, it is the same as the scalar multiplication in vectors, and the only difference is the absence of the commas. For column matrices, again, it's just the same as row matrices, except written vertically. From this observation, we can interpret R2 as the set of all 1x2 row matrices or 2x1 column matrices. For example, the row matrix 2, 5 can be regarded as an element of R2, and the column vector 7, -1 can also be regarded as an element of R2. More generally, we can extend this idea to n dimensions. That is, we can define R to the n as the set of vectors a1, a2 up to an, where a1 up to an are real numbers. Each element is called an n-tuple, and we can interpret R to the n as the set of all 1 by n row matrices or n by 1 column matrices. We also recall the dot product defined in R2. That is, x1, x2 dot y1, y2 equals x1 times y1 plus x2 times y2. We can also extend this idea to R to the n, so that when we have a vector x1, x2 up to xn dotted with another vector y1, y2 up to yn, it is equal to x1 times y1 plus x2 times y2 plus all the way to xn times yn. The idea is the same, in the sense that we multiply corresponding components and then add up the results. We can also rewrite this using the summation notation, which is the sum of xi times yi from I equals 1 to n. Now we begin to formally define matrix multiplication. Let A with entries aij be an m by n matrix with rows Ri, where I equals 1 to m. In other words, we write A in terms of its rows. Note that Ri has the entries ai1, ai2 up to ain. We also have another matrix B with entries bij. It has size n by k with columns cj, where j ranges from 1 to k. In other words, we write B in terms of its columns, and cj has the entries b1j, b2j up to bnj. We define the matrix product AB as the m by k matrix whose ij entry is the dot product Ri dot cj. In other words, the ij entry of AB equals the sum of aik times bkj, where the sum is from k equals 1 up to n. We can write this out as ai1 times b1j plus ai2 times b2j plus all the way to ain times bnj. We can understand what is going on using the following diagram. We have a matrix of size m by n, and is written in terms of its rows, so Ri is a horizontal line of entries somewhere in the middle. we have another matrix of size n by k, and is written in terms of its columns, so Cj is a vertical line of entries somewhere in the middle. When we take the dot product Ri dot Cj, we can imagine rotating the column Cj anti-clockwise by 90 degrees and overlapping it with the row Ri. Since we're taking the dot product, we start from the first entry in each vector and move to the last entry. So for Ri, we go from left to right, and for Cj, we go from top to bottom. The result is an n by k matrix, and the ij entry sits somewhere inside it. Note that for the matrix product A times B to be defined, we must have that the number of columns of A equals the number of rows of B. In other words, the length of the first matrix has to be equal to the height of the second matrix. In this case, the number of rows of A times B equals the number of rows of A. That is, the height of A times B equals the height of A. And also, the number of columns of A times B equals the number of columns of B. That is, the length of A times B equals the length of B. Let's look at some examples. For 1 by 1 matrices, let's say we have a matrix A with entry little a, and matrix B with entry little b. Then A times B is the same as little a times little b. This is because we only have one component for each vector, so we just multiply A and B in the dot product. So this is the same as multiplication in the real numbers. For the second example, which is also the first genuine example, we have 2 by 2 matrices. So let's say A is the matrix A11, A12, A21, and A22, and B is the matrix B11, B12, B21, and B22. Then A times B is a 2 by 2 matrix, and its entries are as follows. For the top left entry, we have A11 times B11 plus A12 times B21. For the top right entry, we have A11 times B12 plus A12 times B22. For the bottom left entry, we have A21 times B11 plus A22 times B21. For the bottom right entry, we have A21 times B12 plus A22 times B22. We can also make things more concrete by using fixed numbers. For example, if we multiply the matrix 1, 2, 3, 4 with the matrix 0, 1, 1, 0, we have 1 times 0 plus 2 times 1, 1 times 1 plus 2 times 0, 3 times 0 plus 4 times 1, and 3 times 1 plus 4 times 0. So we have the matrix 2, 1, 4, 3. We call that multiplication in the real numbers is commutative, that is, A times B equals B times A. So let's see what will happen if we swap the order of these two matrices. So if we multiply 0, 1, 1, 0 with 1, 2, 3, 4, we have 0 times 1 plus 1 times 3, 0 times 2 plus 1 times 4, 1 times 1 plus 0 times 3, and 1 times 2 plus 0 times 4. So we have the matrix 3, 4, 1, 2. And we observe that the two matrix products are very different. So that means that matrix multiplication is not commutative. That is, A times B is not equal to B times A in general. For the third example, let's look at matrices of different sizes. Let A be the 2 by 2 matrix 1, 2, 3, 4, and B be the 2 by 3 matrix -1, 0, 1, 1, 1, 2. Then A times B is a 2 by 3 matrix. Its entries are 1, 2, 5, 1, 4, 11. Notice that B times A is not defined, since B has 3 columns, but A has only 2 rows. For the fourth example, let's look at the multiplication between row matrices and column matrices. Let A be the row vector A1, A2 up to AN, and B be the column vector B1, B2 up to Bn. Then A times B is a 1 by 1 matrix, and it is just the dot product of the two matrices, namely A1 times B1 plus A2 times B2 plus all the way to AN times BN. However, if we consider the matrix product B times A, the result is very different. For each entry of A, when we multiply to the column vector, we create a new column for the matrix product. For the first entry A1, we have B1 times A1, B2 times A1, up to Bn times A1. For the second entry A2, we have B1 times A2, B2 times A2, up to Bn times A2. This carries on until we multiply An to the vector B to have B1 times An, B2 times An, up to Bn times An. And the result is an n by n matrix.